this is a crucial chapter, and in terms of how how to introduce quantum computing. So I'm gonna read through that a little bit more carefully, just to give you a good review in terms of how this is introduced, because I think this is where where most misconceptions or confusion, and people might quickly drop, or give up, if they don't really understand the sort of the basics at the level of the qubits first. So let's see. So you know something about bits, and how you're familiar with computers, digital computers work. It's time to go beyond that. So in modern computers, kind of variables, object structures, blah blah blah. Those are classical variables. And quantum computers, our basic variable is the qubit, a quantum variant of the qubit of the bit. These are quantum objects obeying the laws of quantum mechanics. Yeah, I think that's an important thing, just conceptually, right? I mean, it doesn't really help you long term, but the idea that beats are implemented by electrical signal, right? So a certain amount of electricity gives you a 1, and then non-electricity gives you a 0, and then you can just play with that. Quantum beats can be implemented in different ways. Those are basically things in nature, like at the atomic level, at the quantum level, that behave according to the quantum mechanic laws, and each of those things is an actual qubit. So that's what's important to understand. Essentially, the question tackles, okay, big pastel, blah blah blah. So it's a bit of historical background. This we can probably skip that. I can prove. So I mean, it's important to understand that qubits are kind of variable that is fundamentally different to anything in classical computers. I think that's an important note. It's not that you can just replace qubits with bits. So, okay. As we saw in the last article, we can make a qubit give us a bit in a process known as measurement. So that's called the Z measurement. You're measuring the qubit, and then you get a classical result, 0 or 1. You may notice the small z written at the box. Specifically, okay, there's other ways. Okay, there's an infinite number of possible ways to measure a qubit. So this is just one way, the Z1. To do other kinds of measurements with the composer, you need to use more boxes. So that would be a next measurement. Yeah, okay. So you apply Hadamard, and then it's a next measurement. And that is what. So again, this is again taking the whole thing from a measure, like approaching the whole topic from a measurement approach, right? And I think for me it's easy to think, and that's the way that I kind of built up intuition by playing the Hello Quantum game, and both the app and the command line. Is that for me it's a bit more like I like to understand the qubit as having multiple dimensions, where information can be stored, if you want to use the word, but that might be a bit of a stretch. And so you've got the Z dimension, you've got the X dimension, and you've got the Y dimension, 3 dimensions, and that fully describes a qubit. Sure, you can pick up whatever other ways of looking at a qubit and then define your own dimensions, but that's how I would think, right? So for me, it's like considering that gate as part of a measurement is kind of, I know every single guide out there talks about this way, but it feels a bit awkward because I like from a programmer perspective, you always manipulate information. So the concept of measuring is kind of weird, right? So I think it helps to build intuition, at least from my perspective. If you think about it, you can apply operations to move information between the different dimensions and then measure, rather than, no, you just do stuff and then choose your measurement. I don't know. It's my gut feeling. It basically tells me that. So here is going to give. So we're going to go through an example. Let's do something very simple. Just a single X gate. See what happens. Okay. So you do an X gate, and then you see that that it's always going to give you a 1. And this is maybe that's going to help explain my point of view here, right? So what's basically telling you is, like, here they say, oh look, if you do the same, right, but you consider these being your measurement operation, right? So you're saying, yeah, now you're measuring it from a different perspective. So when you measure it from that perspective, you get that thing where it's going to be 0 or 1 50% of the time. So I like to see this differently, um, as in like this is your operation. Then you move it, you move around. So first you're doing an x to a qubit, so you're flipping it from 0 to 1. Um, and what you're going to do now is you're going to apply a Hadamard gate, which is basically going to move your certainty, your information from the z dimension to the x dimension, right? And then you're going to measure, and then because you have moved that certainty around the second dimension, then now you have uncertainty in the first dimension. But I don't know, maybe because as I'm explaining that, it also raises up a lot of questions on my head. So I don't know if that's a better way of explaining it. But um, check out the Hello Quantum games. I think that's definitely something that you should do. Okay, so this is due to Heisenberg's uncertainty principle. This means the qubit has a limited amount of information, and if it's certain in one dimension, it's always going to be uncertain in another dimension. If you try with an H gate instead of an X, you will make a qubit that is completely certain about what outcome to give for a next measurement, but it will be at a cost. This means the result of the Z measurement, it's uncertain. Yeah, that's the same. It's kind of the same point exactly. You can try other gates and build more complex cases. Mm, for example, cases where the qubit is mostly but not completely certain about what answer to give for both kinds of measurement. Uh, the uncertainty we see here is essentially what Einstein, Podolsky, and Rosen objected to. They thought it meant that quantum mechanics was incomplete. They thought that a qubit always knew what answer it would give, and that it could only seem random because of information hidden in the qubits. So I think that's maybe the biggest. You can summarize this whole thing of um, is it really is the qubits are really something special and different than beats, or no, it's just that we don't know everything about it. um I mean, what let's see how they explain this here. Before we can carry it away, let's look at some cold hard data. So this is like fancy thing, fancy circuit with a bunch of I'm guessing those are rotations uh, from the y-axis, maybe, I don't know. So you're rotating things and then just doing control knots. um, So okay, so this will be discussed later. But what they want to prove is that if you measure that, so you do the measurement. Da, 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 da. Okay, so this is the that's a nice way. So that's a nice way of explaining it. Okay, so that's a nice way of explaining it. This means that there is a result that never occurs. So this is what this circuit has done is it has created a correlation between the two qubits where they will never both be zero. Um, yeah, and then that's an important discovery because why they must have. So they must have been set up in some correlated way to ensure that they never output zero at the same time. This is an important discovery. So let's state it again. The Z outputs of the qubits will never be both zero. Fact one. Now let's look at the qubits in a different way. So now we move that certainty. Yeah. So now we do a next measure. We measure the qubit zero from the x basis, and then okay, and now 1 is never going to be there, but also here I have different probabilities. Mm-hmm. The x output of one qubit and the z output of the other qubit will never be both one. Don't know exactly where they're going, but I think what this is trying to prove is that this is not just some kind of statistical programming, right? Um, Fact 3, the outputs of the qubit will never be both 1. Mm. Okay. Okay, I see. Sorry, I'm just because I'm skipping that. I'm skipping some of the details. Maybe that's the wrong thing to do, but So what they say is if fact 1 says the Z outputs will never be both 0. Fact 2 says the X outputs will the X output of one qubit and the Z output of the other will never be both 1. Okay, and the fact 3 says the X output of qubits will never be both 1, because now we've measured both like that. Okay. Oh. So this is deduced from facts 1 and 2. Okay. Yeah, because we're saying that uh, to prove this, let's think about what it will mean for both X outputs to be 1. We know that an X output of 1 for one qubit must mean that the Z output of the other is 0, because fact 2 tells us that both these outputs being 1 is impossible. Mm. Okay. So if the X output of both qubits is 1, it means that the Z output of both qubits must be 0. Yeah. So it leads us to a contradiction. That's a really neat way of showing that. That's a really, really neat way of showing that. Because then they go ahead and they measure those two qubits and they prove that bam. So there's an 8% chances that this happens. So where did we go wrong? If the X output of both qubits is 1, the Z outputs of both qubits must be 0. We use our knowledge of the X outputs to work out what the Z outputs were. Once we've done that, we assumed that we were certain about the value of both, more certain than the uncertainty principle allows us to be, and so we were wrong. Yeah. It was some non-quantum variable we initialized by some random process. The X and Z outputs would indeed be both well defined. But our qubits behave differently. The uncertainty of quantum mechanics allows qubits to dodge restrictions. Let me see. I have the impression that I haven't grasped that yet completely. So we do first. So we first measure that, and we see that it can never be. The fact 1 says the Z outputs of the qubits will never be both 0. And the fact 2 says the X output of one qubit, because the X output of one qubit and the Z output of the other qubit will never be both 1. So the reasoning goes wrong where we say that we know that an X output of 1 for one qubit must mean that the Z output of the other is 0. Exactly. Because, yeah, the Z output of the other is 0. Because that's what we're saying here. It can never be both 1. This leads us to the contradiction that the Z outputs of the qubits cannot be both 0. So to avoid this result, so if the X output of both qubits is 1, back here up, it means that the Z outputs of both qubits must be 0, which cannot happen. We know that an X output of 1 here must mean that the Z output of the other is 0 because of fact 2. So if the X output of both qubits is 1, then the Z outputs of both qubits must be 0. Yeah, correct. I mean, correct. It's not correct, but it's sort of an it's sort of in a statement that you could make and that's where the mistake is, that um, you're you're basically assuming that you know how those dimensions relate to each other, the z and the x, because you think in terms of a classical system, um, where everything is sort of defined. I think that's it. So if the mistake is saying that if the x output of both qubits is 1, the z outputs of both qubits must be 0. That is not in quantum. So that would be correct at a classical level, but it's not correct in quantum, because the fact that the x output of both is 1, it's not like it's not like a zero something where the two dimensions have to always agree, right? So what this is saying is that the uncertainty that you have in one place is independent from the certainty in the other one. And I think that's what's the weird. That's the kind of the weird one of the weird thing about the quantum world in this sense. So we use our knowledge of the x outputs to work out what the z outputs were. Once we've done that, we assume that we were certain about the value of both, more certain than the uncertainty principle allows us to be. I think that's the key. That's helpful. That's an interesting. I think that's a really practical way of explaining that. I like that, and I like that concept that it's not that you're. So when you think about the different measurements or the different dimensions of a qubit, um, you cannot assume that there's a relationship between them. Exactly. So that's interesting. What else? Our logic would be completely valid if we weren't reasoning about quantum objects. Mm-hmm. They'd just be based on some predetermined list of random numbers, and our computer generated some deterministic process. There would be no reason why we shouldn't use one to deduce the value of the other. But our qubits behave differently. The uncertainty of quantum mechanics allows qubits to dodge restrictions placed on classical variables. It allows them to do things that would otherwise be impossible. So the statement here is an important one. I think it's that a physical system in a definite state can still behave randomly. This is the first of the key principles of the quantum world. It makes quantum computers able to outperform classical computers. Yet another key principle follows this. Two systems that are too far apart to influence each other can nevertheless behave in ways though individually random, are somehow strongly correlated. Yeah, cool. If you'd like to learn these rules, that's nice. Yeah, okay. Play Quantum, Hello Quantum, the Hello Qiskit game, the command line game. Definitely do that. That's a nice way. That's a nice way of introducing why is quantum, why is essentially the logic of the concepts behind the quantum mechanics versus the classical mechanics, why are different, because you would think this is just like statistical programming, right? So you can simulate that easily, but it's not entirely true. That's indeed an interesting introduction to quantum circuits. Cool.